I created a fake account to show y'all this, but these are real CSEC exam questions. I mean, you could do these practice exams all day, and they even knew I was totally confused with this question and recommended this video.
Welcome to this explainer. So, if you've ever been staring down a physics exam question about a fixed volume light bulb and suddenly felt your brain completely freeze over, you are in the exact right place. We're going to conquer that incredibly daunting exam problem together today, and honestly, by the time we're done, it's not going to seem scary at all.
To get there, we're going to tackle this in 4 quick steps. First, inside the gas pressure machine. Second, Boyle versus the pressure law. Third, why Kelvin is absolute king. And finally, solving the light bulb problem.
All right, part 1, inside the gas pressure machine.
Before we get completely bogged down in the math, we've got to ask, what actually is gas pressure? Like, try to imagine what creates that invisible physical force pushing out on the inside of a sealed container. It's not just empty space pushing out, and it's definitely not magic. It is a very real, very measurable physical phenomenon caused by tiny, microscopic actions.
Think of the gas inside a container as a massive, chaotic bumper car arena. You've got a set number of bumper cars. Those are your gas molecules, and they are in constant motion. As they zip around, they are constantly crashing into the walls of the arena. Boom, boom. It's the cumulative force of literally millions of those tiny forceful crashes that creates what we measure as pressure. Now, what happens if you crank up the heat in the arena? Well, temperature is basically just a direct measurement of kinetic energy. So higher temperature means the cars get way more energy, they drive faster, they hit the walls more frequently, and they hit them a lot harder. Faster movement equals higher pressure. It really is that simple. Moving right along to section 2, Boyle versus the pressure law. So we've got our bumper cars sorted out. Now let's see how 2 completely different physical laws handle changing variables. In gas laws, it is literally all about what changes and what stays exactly the same. Boyle's law relies on inverse proportionality, while the pressure law, which you might also know as Gay-Lussac's law, is all about direct proportionality. What does that actually mean? Well, Boyle's law shows that as the volume of a container goes down, the pressure goes up. Opposites, right? But the pressure law shows pressure and temperature moving in the exact same direction. If you heat the gas up, the pressure goes up right along with it. What's super interesting here is the stark physical contrast between the environments you need for each law. Boyle's law needs a flexible environment, kind of like a plastic syringe. You can squeeze the volume down, changing it, while the temperature just stays totally constant. But the pressure law? That one operates in a rigid, fixed volume container. Think of a sealed metal drum or, a glass light bulb. The volume is completely trapped and constant. No gas goes in, no gas comes out. That means only pressure and temperature are left to interact. Which brings us to section 3, why Kelvin is absolute king. Listen, before we plug a single number into an equation, we have to establish the ground rules of the math. Using Celsius is the #1 reason students lose marks in thermal physics. I am dead serious about this. It is the ultimate exam trap. If a question gives you degrees Celsius, you absolutely must convert it first before doing any of your gas law ratios. If you just shove Celsius directly into the equation, your math is going to completely fall apart. To understand exactly why Celsius ruins the math, we have to talk about absolute zero. 0 Kelvin is the theoretical temperature where molecular motion stops entirely. 0 kinetic energy. Going back to our bumper cars, it's the point where every single car just stops completely dead on the track. Now 0 degrees Celsius, that's just the arbitrary freezing point of water. The bumper cars are still moving at 0 Celsius. Because of that, doubling a Celsius temperature from 10 degrees to 20 degrees doesn't actually double the kinetic energy of the molecules. Our math has to start at a true 0 point. So, the absolutely crucial point here is the magic number 273. You must always add 273 to your Celsius value to get Kelvin. The rule is just T in Kelvin equals your Celsius value plus 273. Because in gas laws, K is always king. Seriously, always check your units. All right, final step, section 4, solving the light bulb problem. Armed with our kinetic theory bumper cars and the absolute necessity of Kelvin, we're finally ready to slay the boss problem. A fixed volume light bulb has gas at 293 Kelvin and pressure P. What is the pressure when temperature increases to 360 Kelvin? Right away, you should be spotting the clues here. We are dealing with a rigid fixed volume light bulb, so that's a massive flashing sign that this is a pressure law question. And wonderfully, the temperatures provided are already in Kelvin. Pew! No Celsius trap today. Let's just methodically break this down. Step 1, identify your variables. Our starting pressure, P1, is literally just P. Our initial temperature, T1, is 293 Kelvin. We're looking for the new pressure, which is P2, and our new temperature, T2, is 360 Kelvin. Step 2, set up the pressure law formula. The ratio is just P1 over T1 equals P2 over T2. Step 3, substitute those values and rearrange. So we plug them in and get P over 293 equals P2 over 360. And hey, if fractions kind of freak you out, don't worry, just use cross multiplication to isolate that new pressure, P2.
And there we have it. The final correct answer is P2 equals 360 divided by 293, all multiplied by P. But wait, before we submit our exam, let's just do a quick reality check using what we know about direct proportionality. Always check the trend. Did the temperature go up? Yep, it went from 293 to 360 Kelvin. Therefore, this fraction absolutely guarantees that the final pressure goes up too, because 360 over 293 is definitely greater than 1. The bumper cars got hotter, they're moving faster, and the pressure spiked. It makes perfect physical sense. We've totally mastered the math and the physics today, but I want to leave you with a bit of a mind bender that points right back to our kinetic theory. If absolute zero stops all molecular motion entirely, what exactly happens to pressure when we finally reach it? Imagine all those microscopic bumper cars just freezing in place, totally unable to hit the walls. It is a fascinating extreme limit of physics to ponder. Anyway, thanks so much for joining me for this explainer. I hope gas laws feel way more approachable for you now, and as always, keep questioning the physics around you.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.